Good afternoon, everybody. This talk is going to focus on the RF applications for gallium nitride HEMT. The title of my presentation is Gallium Nitride High-Electron-Mobility Transistors with Thick Copper Metallization for Performance Improvement at Millimeter Wave Frequencies. And this talk has been collaborated with my co-authors, Dr. Lin, Dr. Chen, and myself, and I'm from the International College of Semiconductor Technology, NYCU. This is the way I'm going to organize my talk today. I will start with the introduction first. Mainly, we want to do some broadened view in terms of the necessity for improvement of the RF performance for the devices. Then we go to the section talking about the device fabrication. And I'm going to show you some of the results, and then we have some discussions. And finally will be the conclusions. Okay, introduction. This slide is showing you the evolution of the wireless communication systems. And basically, we start from the first generation, and now we are somewhere in the onset of the very large deployment for the 5G or the 5G generation. And well, the white paper for 6G has already come out. So basically, if you look at the trend, then you immediately see that we start with a very basic voice application. And then we have voice and data. And then we have a lot of many applications adding on, such as video streaming, IoTs, and so on and so forth. One of the very important concepts here that you observe is that actually the system bandwidth has been increasing drastically. Starting from about 30 kilohertz bandwidth required at 1G, we're now talking about almost 1 gigahertz bandwidth at 5G or 5G. And the data rate has also been dramatically increased. The main reason for that is actually the applications. And this application-driven evolution has made the bandwidth requirement to a certain high-level extent. And as I just mentioned, this is actually a so-called application-driven evolution. And this is actually a kind of a roadmap for our deployment of the cellular communication systems. It took about 15 years for the development from 3G to 4G. And then for 4G to 5G, it was about 12 years. And people are expecting that maybe in 8 years, we're going to migrate from 5G to 6G. So actually, the emerging applications have substantially shortened the time of deployment for new systems. And as I just mentioned, that if you go from the very fundamental applications, starting from just voice applications, all the way up to we need the data applications, video streamings, and so on and so forth now, you do see a huge increase in the bandwidth. And actually, currently we're talking about the increasing demands for high data rate and the capacity. And by theory, it is very straightforward that the communication system has a peak data rate of a radio channel in this formula, which is proportional to your bandwidth. And also, the capacity of one radio channel is also directly proportional to the bandwidth. So actually, the key is going to be the bandwidth. So as long as you can acquire wide enough bandwidth, then you should be able to accommodate for all the emerging applications. So this is why we're seeing that almost all the new communication systems are start to migrating their operation frequency to the millimeter wave range. Well, one of the main reasons are basically the frequency bands at C band or below now have been crowded with all the commercial applications. So basically, in order to get a wide, contiguous, clean enough bandwidth for operation to accommodate for very large demand for high data capacity, then we have to migrate to a new frequency spectrum. And this map is showing you the global arrangement for the possible launch of 5G or B5G systems. And they are basically all in the millimeter wave range, starting from around 24 gigahertz all the way up to about 71 gigahertz. So basically, this is going to bring us a certain challenge here, because as everybody knows, when you migrate to high frequencies, then naturally you are thinking about to make your device small in terms of the gate length. And when you shrink the gate length, you are facing a natural barrier that you might suffer from the breakdown voltage. If you can take a look at the very fundamental equation here, that we all know that power is proportional to your current times your maximum voltage divided by 2, then basically we should seek for some device that can have a very nice breakdown voltage in terms of high biasing maximum voltage while applied in this very short channel or very short gate length era. So gallium nitride is one of the solutions, because gallium nitride has the superior material properties that can accommodate for very high electron mobility, very high peak velocity, and this very high breakdown field make it a very nice candidate for maintaining a substantial breakdown voltage while the gate length is small. And gallium nitride for GaN HEMTs are excellent candidates for high power and high frequency applications at room and elevated temperatures due to the material properties. And as a result of improved material growth and processing technologies, actually microwave power densities have been demonstrated that are 5 to 10 times greater than that of corresponding gallium arsenide-based devices. So taking use of this very high density output power characteristics is going to make GaN to be the future mainstream technology for applications at millimeter wave frequencies. And this is actually one of the summary from Georgia Tech, that you are seeing that several device technologies, including CMOS, CG, GaN, GaAs, LDMOS, and the indium phosphide fence. We're plotting the output power, which is maximum output power versus frequency. And here is the Johnson limit there. And this plot is showing all the possible, or actually it's actually open published data. And we're seeing that in terms of the power and the frequency limits, gallium nitride technology has already outperformed a lot of semiconductor technologies. Now let me move into the motivation of this research effort. Okay, and we're showing you the equivalent circuit of a very regular HEMT structure. And as everybody knows that the FT is going to be proportional to your GM, but approximately inversely proportional to the gate capacitances, and then your F maximum is going to be related to your FT by this equation there. And of course, the key parameters there are the parasitic resistance here. So basically, in a way, for the development of devices at high frequencies, then we're caring about the parasitics. So minimization of parasitics is the key for high frequency operation. And the parasitic resistance is of crucial importance, especially at the source, because when you have a source resistance, it is going to act like a negative feedback in the series current path to ground. So basically, one of the possibilities to reduce this kind of source resistance from the contact is by the thick metallization. As long as you have a thicker metallization, then it is quite possible that you're able to effectively reduce the contact paths leading to the source. The second motivation is related to the skin depth, and as everybody knows, when we operate at the high frequencies, then there is basically there are two related topics talking about the skin depth. First of all, the electron flow or the current flow is going to be crowded on the surface, so making it a very bad degradation, since your resistance is going to be higher at high frequencies than low frequencies, because you have less area for the current to flow through. So basically, skin depth refers to, the other term is that the skin depth refers to how deeply an RF signal can penetrate into the material. And this is also pretty much depending on the frequency as well as the material properties. And for the material properties, we are talking about the resistivities or the conductivities of the material. So when we operate at the millimeter wavelengths, then you might have possible radiations at the short wavelength operation range. And these possible radiation may cause severe degradation in terms of some excess unwanted coupling between the traces, or even between the gate contacts or source contacts within the device. So in order to stop the possible radiation causing the unwanted coupling, then also thick metallization is one of the very efficient way that you can use the process to control the thickness such that such effect can be minimized. And the third motivation here is that basically for the next generation communication systems, we're talking about 5G or B5G, and such communication system relies strongly on the beamforming mechanism, and massive MIMO technology has been very widely used. As you are seeing in this picture, this is one of the example that we put on the radar system. And due to the very high loss issue of the millimeter wave range of operation, then you need to have many, many units for beamforming purposes and also enhancing the gain at a certain direction. So usually you are facing a category where you need a super large number of antenna elements and also RF front ends. In other words, within the RF front ends, you need a lot of HEMTs within this circuits. So basically, you're talking about at least 512 elements for a single array there. So basically, if you want to apply for thick metallization, then copper is a very nice choice because, well, you're talking about substantial cost competency compared to the gold. So let's get into the part of device fabrication. Okay, here we are showing you the device structure, including the epi layers and a general HEM structure there. And this is actually the photo of the gate area. We're using a gamma gate here because we use the double process stepper. So basically, the gate area underneath the barrier layer is going to be about 90 nanometers. And the device fabrication process pretty much follows a regular HEMT operation. So we do have major parts, including ohmic contact, mesa isolation, gate formation, and also the thick copper metallization. And our focus will be the thick copper metallization in this work. So basically, all the rest of the process pretty much follows the regular process that we developed in-house. For the thicker copper metallization, we use the 3-time photoresist coating using AZ5214E, and the thickness is about 9 microns. And we use the exposure method to define the pattern. And finally, we use E-gun evaporator to evaporate the composite of these metals onto the contacts. So here is showing you the conceptual diagram of the thick copper metallization process. So first, as we just mentioned, we have 3 layers coating, and then we have the first ABM exposure, and then we do the reverse bake and the second exposure again, and then we do the development, and then diffusion, and then finally we do the level. So we have the TI layers there to enhance the adhesion ability between PT and the ohmic, as well as the adhesion of CU and PT interface in this study. And this is the final picture for the thick copper metallization. And we estimated the thickness to be about 9 micrometers, and the practical measurement is showing somewhere about 7 micrometers. And now I'm going to share with you the device results and then discussions. Okay, first is the contact resistance measurement. So basically we'll use the TLA method, and we have 2 lines here. The green line is with thick copper metallization, and then the red line is without thick copper metallization. And basically we have curve fitting using a linear curve fitting method, and basically the extracted values for the contact resistance are 2.5 times 10 to the minus 6 ohm cm squared for the device with copper metallization, thick copper metallization, and 1.7 times 10 to the minus 6 ohms centimeter squared for the device without thick copper metallization. And this slide is showing you the comparison of the DC characteristic in terms of the IDS VGS curve and the GM VGS curve. The device size was 2 by 20 micrometer, 2 fingers with each finger of 20 micrometer long. On your left-hand side, you're seeing the device with thick copper metallization, and on your right-hand side is the device without thick copper metallization. The measurement was taken at the VDS equals to 10 volts. As you can see, for the device with thick copper metallization, we do have a slightly higher GM in terms of the external maximum GM for the value of 380 microsiemens per millimeter, whereas for the device without the thick copper metallization, the maximum GM was measured to be 350 microsiemens per millimeter. And basically the maximum IDS is comparable for the one with the thick copper metallization. We have close to 1.1 amperes per millimeter current density, and this one is just slightly lower than the one with thick copper metallization. And basically the on resistance was also extracted. Again, we have the same device size of 2 by 20, and the R on for thick copper metallization was extracted to be 1.53 ohm micrometer, and that for the device without thick copper metallization was extracted to be 1.67 ohm micrometer. I'm showing you a very simple kind of circuit-wise explanation of the effect of this RS. So in general, you can express your intrinsic gallium nitride HEMT device as a black box here, and then you can get the whatever equivalent circuit model based on the S parameter measurement, and then convert to the Y matrices. So you can relate the current and the DCGM with all the intrinsic components as well as the external parasitics. So basically you're seeing that actually your RS prime and RD prime are given crucial importance, because you can see that if you can reduce RS prime and RD prime, then you should be able to increase your current and your maximum transconductance, as we just saw in the previous slide. Now I'm showing you the RF characteristics, and we use the on-wafer S parameter measurement to characterize both devices. Again, on your right-hand side, we're comparing the FT, which is the unit current color frequency. So basically, we again have two lines. The black one is the one without the thick copper metallization, and the red one is the one with thick copper metallization. And the extracted FT of the one with thick copper metallization was 42 gigahertz, and then the one without thick copper metallization was about 32 gigahertz. For F maximum, we use the extrapolating technique. Again, we take the MSG and then do the frequency plot and take the log scale. So again, the black one is without thick copper metallization, and the F maximum is about 100 gigahertz. And the red line is correspondingly the one with thick copper metallization, and the extracted F maximum is about 115 gigahertz. And we also did some modeling to see the real effect that caused the increase in terms of the FT and the F maximum for the device with thick copper metallization. And I'm listing all the important parameters here. So basically, as you can see that for the device with thick copper metallization, we are actually seeing some substantial reduction in terms of the CGD compared to the device without thick copper metallization. And this is actually one of the key leading to the increase of FT, whereas we see a smaller RS and RD levels for the device with thick copper metallization. And this is also the reason that we do have some increase in terms of the F maximum. And this is the low pool measurement. And we're seeing that for the device with thick copper metallization at the 38 gigahertz, we're having a maximum output power about 6 watts per millimeter. And for the one with, we have a similar output power density, and these are all taken at 20 volts. And here is a table showing you different device sizes, and we do get a very nice power density when the device is at 2 by 15 micron, and we can get up to around 8 watts per millimeter when the device was 2 by 15 micron. And this is the conclusion of my study. In this study, the copper metallization technique for GaN-HEM device operating at millimeter wave frequencies has been realized, and we use the thick copper metallization to reduce the RS prime and RD prime such that we can get the improvement in terms of the DC and RF characteristics. And the experimental verifications revealed that the device with 2 by 15 micron gate width exhibited the maximum output power density of 8.2 watts per millimeter, and this is comparable among the state-of-the-art results at Ka band published up to now. And such superior results have proven the feasibility of integrating this thick copper metallization process in the device to make it promising for the next generation communication system applications. And these are the list of the references of this study. And thank you very much for your attention.